All right, I'm going to discuss how logistic regression works in this video, but before that, it is really helpful to summarize our understanding of ordinary least squares because it is very closely connected to the concepts in logistic regressions. Well, let's refresh our minds about the example that we worked on in the previous video. In the OLS example, the task was to see how much a student can improve his grade by increasing the number of hours studied by 1 unit. So we had data on a bunch of students about the hours of study. This is the feature, and also their grade, which is the outcome. And when we plotted them, we realized that we can run a straight line through these lines and find the equation for that line using the sum of the squared errors. Now, how about the situation where instead of looking at the final grade as a number, we look at the outcome as a binary outcome. So whether or not the student has passed the class rather than looking at their final grade. And now this would introduce an immediate challenge, and that is when you plot this outcome, the binary outcome that can either be 1 or 0, then you no longer are going to have that extended range of values. So whereas in the OLS example, the outcome, which was the grade, was ranging anything between 0 to 100. So you could have the possibility of having, say, 55 or 65. In theory, you could even have lower than 0 and higher than 100. And there could be any number in between 0 and 100. However, in this example, you could either have 0 or 1, meaning that the student would either pass the exam or not. There is nothing in between. There is nothing like half past the exam, right? So here, when we're looking at the outcomes, there is a bounded variable, the binary outcomes. There is only 2 outcomes, right? So that is the first challenge that we have to deal with. And the solution, the way that we deal with that challenge is to transform the y-axis from probability to log odds. And the unique thing about the log odds is that while it is related to probability, it is not bounded between 0 and 1, and it can actually go from negative infinity to positive infinity. And this is the very simple formula to calculate the log odds. And we have talked about this in the previous videos as well. So log of odds of passing could be calculated as the log of the ratio between the probability of passing and 1 minus probability of passing. Now let's look at this using the example that we are working with. So this is the scatter plot of the data that we have. Some students did not pass the course, whereas the others passed the course, and they are plotted in this scatter plot with 0 and 1s. Now, this is the probability of passing. So 0 for those that did not pass and 1 for those students that passed. Let's start with the middle point, the 50% probability. If we want to calculate the log odds, then we're going to use our trusty formula, which is the log of probability of passing divided by 1 minus probability of passing. So for this point where the probability is 50%, if we plug in the numbers in the formula, we would have a final answer of 0, because the log of 0.5 divided by 1 minus 0.5 is equal to log of 1, which is 0. So we can start this new plot, which we call it the log odds of passing, and the equivalent point for 0.5 probability would actually be here, would be at the point 0. Now, how about say this point, which is about 75% probability of passing? Again, if we put that into the formula, we get a log odds of 0.47, and we can show it on the plot for the log odds. And we can do that for any other probability on the y-axis here. So this one is, for example, for the probability of 95% for passing, and the log odds would be 1.28, which is somewhere around here on the y-axis for the log odds of passing plot. And, when we get closer to 1 for, say, 99%, the log odds would be equal to 1.99. Now, interestingly, when you go below 50% for, say, 25% probability, the log odds would be negative. So here we would have negative 0.47, and we would have negative 1.28 for the 95 probability. And when we have, say, a probability of 5%, the log odds would be negative 1.28 as we have here. And as we go even further and look at the probabilities of 0 and 1, you would notice that that would be positive infinity and negative infinity. So for a point here, when the probability is 1, for all these students who have passed the course, we will actually get a probability of positive infinity, because log of 1 divided by 0 would be equal to log of 1 minus log of 0, which is 0 minus negative infinity, which is equal to positive infinity. So these points, the students who have passed, if you want to plot them on the log odds plot, are going to be equal to these points. The interesting thing and important thing to note that is that their y value, the y-axis or the log odds for these points, is going to be equal to positive infinity. And if you do the same for these points who are at 0 probability of passing the course, then you are going to have negative infinity, as I've shown here in the calculations. So these are going to be the points that are equivalent to the students who have failed the course or have not been able to pass the course. And this would be, the mirroring of plot of probability to a plot of log odds. And then you would see that while probability is a nonlinear function of the features, log odds can be a linear function of the features. Let me show you with a better example. So this is a set of probabilities that I've just created in Excel, and they start from a very small number, almost 0, to a number that is almost equal to 1. And for each of these probabilities, I've calculated the log odds using the formula that we were working with right now. So for example, for a point of 0.5, the log odds is 0, and I've calculated the rest accordingly. Now, if I plot the probability, you would see that we have something like an S-shaped function. And if I plot the log odds, you would see that it is a linear function. So that is how the probability would transform to a linear function from a nonlinear function. Now, while the transformation that we did here solves the first problem, and that the first problem was that there was no values in between 0 and 1, and transformation to log odds solves that problem, because now we are actually going to have values between 0 and 1, and more importantly, we're going to have values more than 1 because it goes up to positive infinity, and values less than 0 because it goes to negative infinity. So we've solved the problem with the bounded dependent variable, or the bounded outcome, by using the log odds transformation. We're still going to have a very big problem. And the big problem that we have is that we cannot calculate the sum of squared errors to find the best line, as we were doing in the OLS regression, simply because all of these distances are positive and negative infinity. So we cannot add them up together. It's not going to be meaningful to add a bunch of positive infinities to a bunch of negative infinities together, right? So we could not use the same technique of minimizing the sum of squared errors to find this straight line, right? Because now with the transformation that we have done, we still need to figure out what is the best line that fits our data. And we now know that we cannot use the minimization of squared errors as an approach to that. So what should we do? Well, the solution is to transform the log odds back to the probabilities using the formula below. And again, this formula should look familiar to you because this is the one that we've been using when we were discussing gradient boosted trees. So what this formula does is that basically it reverses the logit function, right? It transforms the log odds back to the probabilities. And this basically the solution that I'm going to talk about is the maximum likelihood estimation strategy. So let's see how it works. So this is what we have. This is the plot of the log odds. We have our points on the plot, and we want to figure out what is the best line that fits this data. And let's suppose that the green line is the line that we are starting with. What we are going to do is that for each of the points, we are going to first find the log odds. And once we have found the log odds, we are going to use this formula to transform that log odds back to probability. So for this point, when you look at the log odds given based on this hypothetical green line, you get 0.47, and then when you plug it back to this formula, you get a probability of 0.61. Now you can plot that in a scatter plot. So between here, between 0 and 1, because we are working with the probability. And for the student that has been studied about 23 hours, this guy here, the probability, assuming that we are working with this green line, is going to be 0.61, and that is the y axis for this particular point. Now you can do this for all of the points that you have, or for all of the observations that you have in your data set. So for example, for this guy, if you assume that this green line is the best line that can fit the data, you can figure out what is the log odds, and it looks like it's about -3. And then you can transform the log odds back to a probability using the formula and get the value of 0.047, which is going to be about this line, right? So once you do this for all of the observations in your data set, you can fit you can have a line that goes through them, and then you basically can calculate the likelihood. What does it mean? It means that you're going to calculate the likelihood of observing the data given the shape of the dotted red line, right? So for each point, now you're going to have a likelihood, and you're going to multiply all the likelihoods together. For each point, you're going to have a probability, and once you multiply the probabilities of all those points, meaning that the y-axis dimension of all those points together, you are going to have the likelihood. Now you can rotate this line and have an alternative line. So what if instead of the green line, now you have this highlighted line? Well, you're going to do the same. You're going to calculate the log odds for each point, transform them into a probability, plot them on the line, and then instead of having the original initial red dotted line, you're gonna have, say, a blue line, right? And then based on the blue line, you can calculate the probabilities for each of these points and multiply them together in order to get a new likelihood, right? And basically, the task at hand is going to be to choose the line that has the highest probability. Choose the line that gives you the maximum likelihood of observing what you're observing, and that is done by an algorithm. And by the way, rather than using the likelihood, you can also use the log likelihood it is mathematically simpler and easier to use the log likelihood, and the line that maximizes the likelihood is also going to maximize the log likelihood. So it really doesn't matter whether you take the likelihood or you take the log and use the log likelihood. That would essentially determine the line equation of y is equal to a plus bx. So it will give you the intercept and the slope for the log likelihood line, which is what you are looking for.